To introduce our next speaker, Nalini Joshi from Sydney University, and as you can see, she'll speak about why she loves elliptic curves.
Thank you very much, Marianne. Thank you to the organizers for inviting me to speak and be involved in this beautiful event. So I wanted to start with some reminiscences and then give an overview of the two halves of elliptic curve theory that are important in my area. And so if you have any questions or want more details, please don't hesitate to stop me. Now, so going back right to the beginning, I met Rodney Baxter, when he came to the meeting that was held at the Institute for Theoretical Physics. Now it's called the Kavli Institute for Theoretical Physics at Santa Barbara in January 1985, which was held to celebrate Martin Kruskal's 60th birthday. It was an amazing event. I was a graduate student at the time of Martin Kruskal's, and I was there for that meeting and for several months afterwards for the program they held there. Rodney was a wonderful reminder, I remember, of Australia, not only the way he spoke, his voice and style, but his ease with the mathematical methods that I was familiar with from my undergraduate days at the University of Sydney, as well as his intimate knowledge of elliptic and other special functions. So after that meeting, there was a volume of papers that was collected from the speakers at that meeting. And this is Rodney's paper. I'm sure many of you already know about it, but that volume is worth looking at in print because the different parts of the topics were collected with a little bit of an epigraph, which included the limericks that were written out and spoken out loud at the conference dinner for that event. So it's worth looking for that quirky reminder of what it was like in those days. So at that time, as I said, I was a graduate student at Princeton. I was exploring how the asymptotic behaviors of the Pain-Levé equations arose. And in the way we saw things, it was intimately tied to elliptic curves, not just one curve, but curves that changed with time. And I'll come back to a little bit more detail about that in a while. But what struck me was something else that came from Rodney's point of view. And when I moved back to Australia, to the Centre for Mathematical Analysis at the Australian National University, I think many of you visited later on. In 1987, I met Rodney again. And I think it was a couple of years later, in 1989, there was a summer meeting on exactly solvable models. And he was arranged to give several days of lectures, but he was unwell at the time. I think he'd had maybe a heart attack. And so he wasn't there, but he was there in spirit through recorded lectures, which I think Jacques already referred to earlier for another meeting. They were spoken by his wife, Elizabeth, and that was, I remember finding those lectures eye-opening. So what was eye-opening about them was that there was this underlying view of elliptic functions and the identities that they satisfied, which are collected in chapter 15 of Rodney's book, which I have a copy of. And I think it was Peter Forrester said that he looked at, was it chapter 13 on corner transfer matrices quite often? Well, the one I look at very often is chapter 15, and I still find myself reaching for that book, even now, so many years later. So what was it that struck me? Well, the fact that these complicated identities, which people had collected over many decades, if not centuries, for elliptic functions and theta functions came from such a simple setting, such a simple beginning. I think Rodney starts with Liouville's theorem, which is that well-known theorem which says that if you have an entire function which is bounded everywhere in the complex plane, then it must necessarily be a constant. And he applies that theorem over and over again to combinations of theta functions, which are, of course, entire, and he's able to deduce multiple identities from that very simple beginning. So in that 1989 program, there was this meeting, which I took this screenshot from Murray's slides, the first talk of this conference. And you can see there, I think, Murray, was it 10 people from this picture are attending this meeting. I
Yes.
met so many amazing, great mathematical physicists. And I'm standing in the back row, in case you don't recognize me, next to Jacques Perk, between Jacques Perk and Catherine Seaton. And in the row in front of us, there's Barry McCoy, third from the left, Tony Bracken at the extreme left, whom I met again many years later. And of course, Peter Forrester between them. And in the front row, next to Rodney, is Reinhard Quispel, who's speaking after me, and as well as luminaries like Jimbo and Miwa, Paul Pierce next to Jimbo, and so on. So Reinhard Quispel, I remember, told me, because he was also at the ANU at the time, he told me about the maps that he and John Roberts and Colin Thompson had discovered and were formulating in generality, which are now referred to by their initials as QRT maps. And they are fundamentally grounded in theorems that hold on elliptic curves. And I'll come back to that point of view as well in a little while. I met Barry at the meeting I referred to in Santa Barbara, and that's another very distinctive, memorable occasion, which I'll let him talk about at some point. But there were so many people there who already knew so much about Pavlov equations and their asymptotics, their connection problems, their identities. What I was doing seemed very small in comparison, but nevertheless, that deeper point of view of elliptic curve theory led me somewhere that I think turned out to be a little surprising later on. So let me start with that story, the story of elliptic curves. And elliptic curves have a very long history of their own, of course. This is an example of one that I've drawn, graphed in the real plane, in the XY plane. For you with this simple choice of parameters. So all elliptic curves have a canonical form, and the canonical form is given by a cubic polynomial, and you can write it as a cubic in one of the variables and a quadratic in the other. And here you see that with x being the variable of the cubic and y being the variable of the quadratic. And I chose these numbers because this is easy to draw in the real plane. So for example, when y is 0, you can immediately see that x must be either 0 or x squared must be equal to 3. And you see those points at the intercepts of the horizontal axis here. So they intersect the x-axis at plus or minus square root 3 and at 0. And because we have only the term y squared, it's symmetric across the x-axis. So this is an example of an elliptic curve. And they arose in many mathematical physics, I would call it, settings, going back to planetary motion, Kepler's law, which describes the orbits of planets around a sun at one of the foci of the orbits as an ellipse. And questions that were asked about how to describe the arc length that they traverse on a planetary orbit or the area they sweep out. And there's some astonishing results of Newton from that time, which are worth going back to, I think. For example, he shows in Lemma 28 of Principia Mathematica that the arc length drawn out by a planet around the ellipse can't be a solution of any polynomial equation. In other words, it must be a transcendental function of the argument, the angle of location of the planet on that orbit. So there are a huge number of other results that are now known for the functions that parameterize this curve. If I take any point xy on such a curve, I can now think about writing its parameterization in terms of elliptic functions. I take the canonical curve to be of this form, which means that the parameterization is given in terms of Weierstrass P functions with the usual parameters G2 and G3 associated with the curve being given by 12 and 0 in this particular case. You can, of course, rewrite this equation in terms of either a quartic in X or in terms of biquadratics, something that's degree 2 in X and degree 2 in Y. And that last formulation is important for QRT maps. So suppose I don't just stick to one such curve, but I now think about bringing in that third parameter, G3, and allowing it to be free while the component that I'm showing you here stays the same. When I do that, I get what's called a pencil of elliptic curves. Pencil because I have one free parameter, which I call K on this slide. And as I go around, go from one value of K to another, I will move from one component you see on this picture to another component and another component, and so on. So I am actually traveling across these lines, these curves, as K is changing. But nevertheless, on each such curve, I still have the parameterization in terms of the Weierstrass P functions in the way that I've shown you there. Here, the dot means d by dt. So I have such an elliptic pencil, and it turns out that this is what underlies the motion that you see in the nonlinear second-order differential equations called the Pain-Levé equations. Let me give you a specific example in a moment, but before I get there, let me also remind you that although I have this continuous motion in terms of parameterization in T, I also have discrete motion through the addition formula. The addition formula is shown here. It comes from intersecting one such elliptic curve with a straight line. So if I have two given points, I can draw a line through them, through P and Q. It will intersect the curve again because it's a cubic curve. There's a third point of intersection. And the convention is that you take the reflection of that point to give you what's called the addition of the 2 points. And this forms a group action with the group element that is the point, the identity element being at the point at infinity. So there is both a continuous motion on the curve and a discrete motion on the curve. And this gives rise to discrete Pain-Levé equations. So let me show you the first half of that story with the first Pain-Levé equation. Here it is, the ODE that's on the top left of the slide. This is the first Pain-Levé equation. Deceptively simple, but incredibly complicated. It is of interest in physics because it arises in many settings, including matrix models, quantum gravity, and so on. All of its solutions are higher transcendental functions that are more complicated and therefore newer than elliptic functions. But at the time I was studying them, we knew hardly anything about their solutions globally. So the main information we had came from a work of Boutroux in 1913 and numerical explorations. So here is a snapshot of a numerical exploration of a solution with real initial values. So this is in the complex X plane. And the jagged edges are just where the numeric stopped iterating. So you can see what you see with the little open circles are the locations of the double poles of the solution. And you can see that they are arranged in this very pretty five-fold pattern in the complex plane. And that's because the equation itself has a discrete five-fold symmetry. And if I wanted to know more about the deeper mathematical properties of the solution, what was happening around that time with the work of Jimbo, Miwa, and then the Russian school of Itz, Kitaev, Kapaev was through the linear problem, the associated lattice pair, and the monodromy problem. But I needed to know more about the solutions. And what I started with was, first of all, to look at Boutroux's coordinates. And that's easy to implement. You take this change of variables from W to U and from X to Z. I'm going to write it in system form because it's slightly easier to look at geometrically. And if you make this change of variables and rewrite d by dz as a dot, then you have a system of equations like this. And this makes it easier to look at the asymptotics as the independent variable z is going to infinity. But if z does go to infinity, the last terms on the right-hand side drop out. And what you get is an autonomous differential equation, which happens to be solved by elliptic functions. In fact, the Weierstrass P functions. And the interesting thing here is that this system is a Hamiltonian system, regardless of the fact that it's not autonomous. So the energy E can be written down as a polynomial in U and V. But because this is a non-autonomous system, this E is not conserved. It gives you an elliptic curve with what I previously called the parameter K replaced by 2 times E. But that E is changing with Z. So what you have are elliptic curves that are modulated as E changes or as Z changes. We're moving from one elliptic curve to another as the independent variable of the Panavert equation changes in the complex plane. And this was the starting point of a lot of exploration. In particular, if I now think about the picture of the pencil of curves that we had as one slice of this story, this motion in the Z plane, what we get are successive slices of that pencil with motion from one point on an elliptic curve to another point on the elliptic curve and so on, moving continuously through this, what's called the initial value space. Technically speaking, this was constructed by Okamoto after resolving all the singularities. In particular, for this example, these are singularities at infinity. But in any case, what you get is now called Okamoto space of initial values. And you get an algebraic structure in this space, which characterizes the equation and its solution. So for the first Panavert equation, that structure is given by E8, the exceptional Lie group of rank 8, and its affine version, E81. So there might be connections with Paul Pierce's talk earlier where he was explaining the ADE descriptions of many models. So the algebra geometric study becomes important here. And what Okamoto did was purely algebra geometric, but we wanted to try and use it to try and understand the dynamics, to understand solution space for the Panavert equations for things that were not available through looking at lattice pairs and inverse monodromy methods. What we found was for we've done what seems like a very long-winded story now, but anyway, we completed the story for all the Panové equations. We found a repeller set in the initial value space. We found that the numbers of movable singularities of the general solution must be unbounded. So there's an infinite number of movable poles, for example, that there exists a complex limit set, and so on. And the whole story is outlined for each Panové equation in this series of papers, with the story only finishing a couple of years ago. So what's new? What's new is the discrete story. And let me now just go through fairly quickly, in summary, the discrete part of this story. In this story, and what's new, it comes from the QRT maps. So QRT maps, again, what I've drawn here is an elliptic pencil, but not for cubic curves, for biquadratic examples. If you outline one such elliptic curve in orange, and then take a horizontal line through the curve, that gives you a mapping from one point to another, often labeled by the Greek symbol iota 1, let's say. And then you take a vertical line through that image point, then you get iota 2. The composition of those two maps are what gives you a QRT map. And you can write down what Q, R, and T showed was that you can write down these all the information in a very clear and beautiful way by using two matrices, 3x3 matrices called A here. And that mapping has an invariant, which is written in this form, with capital X and capital Y being vectors that are quadratic in each variable. So that's a lovely story, and it's that story that was generalized. First of all, I'm sorry, I skipped the fact that the maps can also be written down explicitly in terms of components of these cross products. So this story was hugely influential, and it was generalized by Sakai at the University of Tokyo in 2001. And by generalizing it through algebra geometric descriptions, he found 22 classes of systems, which include the differential Panové equations and the discrete Panové equations. So the example I gave earlier, the first Panové is right down here in the bottom right corner. These represent the root systems that correspond to the structure of the initial value space. So it is important now to understand whether this diagram could be extended. And one way one might go about extending it is to see if there are extensions of QRT maps. And this is the work I've been doing very recently with Frank Neyhoff and Alan Steele at the University of Sydney. Frank was until recently at the University of Leeds, and now he lives in Leiden in the Netherlands. And I want to point out to you that here that the same way that you have exactly solvable models with elliptic cases, trigonometric cases, and rational cases, you have here a characterization in 3 families, which are also very important. So how could one generalize? So if I go back to my cubic form of the curve, I can again take a straight line, use the addition theorem to define a map. Now, instead of taking the second part of the map being on the same curve, I can do an addition on a separate elliptic curve, characterized in a similar way with the addition theorem, but where the second map is in a different space. So the first one is in terms of little x and big X, and the second one in terms of little y and big Y. The elliptic curves are not necessarily the same curves. You can look at this in multiple ways, but the simplest way is to think about the parameters being independent of the other variables. If you do that, you still have An invariant, you still have a matrix description. You have parameters coming from the 18 entries of these two 3x3 matrices. We require that the what I'm going to call capital Phi and capital Psi lie on the elliptic curves. So that gives you conditions on the entries of these matrices. And miraculously, what we discovered by using the huge power of MAGMA, which is a symbolic algebra program developed at the University of Sydney, was that we could find solutions to all of these conditions. And that was a very, very nice surprise. So we have explicit matrices that satisfy these conditions that generalize the QRT map in a very similar way to the setting of the QRT map. But instead of having little x squared, we have a capital X, little y squared, we have a capital Y. We're working in 4-dimensional space, but we have these conditions that give us a surface on which we are iterating. And there are some other things that come along for the ride. We can show that the composition is a symplectic map. It preserves this invariant, which looks very similar to the one from the QRT map. But you might want to see an example just to make sure that what I've described to you is not an empty set. Here is an example with integer entries in the matrices. You can decide for yourself how to show that the structure is self-consistent. It's self-consistent under certain conditions on the parameters of the elliptic curve. And I've drawn those examples here in 2 colors, where the first one takes little g3 to be 0, and the second one takes capital G2 to be 0. And the invariant looks like this. So in this example, we have, as you can see, degree 1, invariance in the 4-dimensional space that we have. But if you were to replace capital X and capital Y by using the elliptic curves, what we have is an algebraic function. So our hope is that this will lead somewhere more interesting with more examples to come. But at the moment, the referees are not agreeing with us. So hopefully we'll get somewhere anyway. So let me come to an end now. I've given you a story that I hope shows you how the differential Pain-Levé and the discrete Pain-Levé might rely on elliptic curves. In fact, they underlie, in my view, every aspect of these equations, and there is still more to be discovered about that connection. And Rodney had a huge influence because he had strikingly simple starting points for understanding elliptic functions and elliptic function identities. Many open questions, I think, remain about, but in particular about the discrete or difference Pain-Levé equations. There are examples that seem at first glance not to fit in Sakai's diagram, but that turn out to be kind of like folded versions of the root systems in Sakai's diagram. That's an important direction that many people are pursuing. Or if you give me a discrete equation that you think might be important, perhaps arising from the setting of statistical physics, how to identify it as a Pain-Levé equation, discrete or differential. All of those are fairly open directions of research at the moment. But my hope is that there is even more fundamental things remaining to be discovered. And I want to end by thanking Rodney for the beginning that he forged for me. Thank you.
Nalini, thanks for a very clear and wonderful talk. Do we have any questions here?
I can see one from Peter.
Peter, do you want to
I was just
Yeah.
about to say, hopefully this time I can be heard, but history repeats. So
Yes.
thanks for such a beautiful lecture there, Nalini, and passionate one too in relation to Rodney and all things that he's left us with. I was just going to say, I had a question formulated during your talk, but you sort of, maybe it's only a comment now because you said near the end there that you're actually being led to hyperelliptic functions. And why I asked that is that when Rodney was studying the chiral Potts model, he wrote a series of papers on parameterizations involving a hyperelliptic function. So I sort of found that very, let's say, futuristic. It was sort of one of the last series of very mathematical works that Rodney put out there. So maybe it's only a
Okay.
comment, but I think it's worth very much highlighting that you're being led to that from a particular viewpoint, and Rodney was led to the elliptic functions through the chiral Potts. So please let me put that out there just as a comment, given what you've already said about your findings in relation to hyperelliptics. So,
Thank you very much, Peter. I'll look them up.
very good.
Do you have any other questions here?
Well, I actually, sorry, hi, Nalini, for a wonderful talk.
Hi,
I
Ollie.
actually had a question which was very, very closely related to Peter's remark, because I also wondered about hyperelliptic functions. Now, of course, the problem is we no longer have a group structure on those, which seems to be crucial for what you're doing. But there's the notion of the Jacobian of a hyperelliptic curve, and they do allow for a group structure. So I wondered if that gives you enough to indeed push this beyond the elliptic case. But it seems like this is not known yet, or...
No, it's somewhat open in my mind. I don't know yet whether I'm being led to hyperelliptic curves or simply products of elliptic curves, if you see what I mean. There is a structure in bielliptic surface theory which we haven't quite exploited yet. And so bielliptic surfaces come from products of elliptic curves, but they are quotiented out by a symmetry group of the each curve. And they used to be called, confusingly called hyperelliptic surfaces, but now they're called bielliptic surfaces for a reason that escapes me. But so there is a kind of open question here. I don't know yet whether I'm heading for a higher genus and potentially group structure on the higher genus curves, or whether I'm being led back to elliptic curves, but just kind of augmenting them in a different way. But yeah, there is a part to it which I haven't explained here because it's too technical, but there is a way to get back to QRT maps from this story of the bielliptic surface maps by taking singular limits of the elliptic curve. So if I take this, the singular limits of these curves, then I get back to straight lines. And these straight lines lead me back to QRT maps.
Yeah. Sean Murray had a comment.
It's more common when you look at higher genus curves. Of course, one has to look at Jacobian, and as Ole mentioned, I mean these Jacobians are not very well understood in the hyperelliptic curve. But I suspect we have some what's called the split Jacobians. Namely, these Jacobians turn out at the end of the day to be a product of elliptic curves. You have examples of that for genus 2. There aren't so many for higher genus. So typically the Fermat curves occurring in chiral Potts. So, but I suspect that's the situation we have, namely Jacobians that turn out to be split Jacobians, namely product of elliptic curves. And also, I think that's the reason why this K popping out in the cow pots. It looks really like the modulus of the we have on the Bax model or the housing model, which is a genus 1 situation. But probably that's because the Jacobian is there is an elliptic curve hidden somewhere in these Fermat curves. That's well, personal opinion, but
I'd welcome people sending me links to relevant papers. So please email it to me. Email me links. John Roberts put one in the chat too, I noticed, and happy to look at all of that and learn from them.
Okay, then, on that note, thanks again, Nalini.
Thank you.